Good morning, Mustangs. Welcome back to another edition of No Here, No Problem. This is going to surprise you. I literally have been using Zoom for I have no idea how long, and I just figured out how to change my background. So I decided to put on a nice scenic view for us, whereby it's getting colder out. You know, just thinking about something that is warmer and just more I don't know, scenic and beautiful. And I saw this, I was like, this is stunning. So I decided to add this. You know, give us a better setting. Today, we are going to be starting a brand new unit. For us, it's a new unit, but in general, this should actually serve as a really good review. We're going to be doing exponentials and logarithmic functions, and we're going to be talking about, first of all, we're going to be starting with just basic stuff, you know, just the basic properties, reviewing all the stuff that you guys know, getting through the fundamentals, and then we'll be diving into a little bit deeper stuff with this, okay? We're combining the first two sections because section 3.1 dealt with exponentials, section 3.2 dealt with logarithms, so it only made sense to just put them together since they're kind of tied together. So let's get started. All right. If I gave you a general problem like this, let's say I had 5 to the x power is equal to 3.2645, right? Okay. If I gave you this, let's say it was 5 to the second power is equal to 25. Oops, nope, not what I wanted to say. 5 to the x power is equal to is equal to 125, you would know this one offhand. You would know that the x value is to third power. That's because 5 to the third power is 125. When we get to these weird wonky decimals like this, how do we go about solving them? We can't just sit here and keep guessing and checking. In fact, if I was to pause the video for you, or if you were to pause the video and just start typing in values for x until you eventually got to the answer to 7 decimal places, I bet it would take you several minutes. The fact is that the answer for this is actually x is equal to 0.735115563. Okay? Now, how do we get that so quickly? Well, whenever we have a variable in the exponent, what we're going to do is we're going to convert it over to what we call log notation. And really all that is an inverse operation of an exponential. Now, remember when we talked about inverse operations, we take the x's and y's and we swap their places, and then when we solve for y again. So take a look at this problem right here. When we look at log base 5 of x and we look at 5 to the x power, believe it or not, these are actually inverses of each other. Let me jump over to our graph right here. Whoops. This is where I want to go. Let's start with just first the very basic problem here. Let's talk about y is equal to 2 to the x power. This is what we call an exponential function, meaning that as x grows, it grows the value for y grows very quickly. And when we look at y equals 5 to the x power, it just means it's going to grow even faster. Well, why is this? When we look at the, gosh, hang on, I got to clear that out. I don't want to keep swiping to that. There we go. Okay. When we look at the, just accidentally closed my decimals. No. All right. Well, I'm going to retype these in here. Y equals 2 raised to the x power. Y equals 2 raised to the x power. And then y equals 5 raised to the x power. And then we had y equals... Now, to do the log, I'm going to actually move myself out of the way here so you can see this. To do the log, we're going to use the function button on the right side there. And to do that, then you go all the way down to the bottom here where you see calculus, and you'll see it says log. There's an there's an option there when you look at it where it says you can do ln, which is natural log. You can do log, which is just straight log base 10. And then you got this log right here, which is log base. Okay, we're going to use log base. And we're going to say 5 of x, okay? And then I had one more equation on here, which is y is equal to x, okay? And I'm going to make that dotted. There we go. All right, we're back in business, people. So when we look at the graph of y equals 2 to the x power, that's the red one there. You can see it grows. And then y equals 5 to the x power means it grows even faster. And when we look at the domain and the range for this, you could see that for the domain, it goes to the left, and it just goes to the left forever. I'll spare you the trouble of looking at the graph. It goes to the left. And when we look at to the right, it'll go to the right forever. It just grows very quickly as it goes to the right. It goes up forever, okay? the domain doesn't change for y equals 2 to the x or y equals 5 to the x. It goes to the left forever and it goes to the right forever. You can't really see the right side too well because it goes so quickly to the right and up. Okay. Well, what about the range? When we look at the range for this, it goes up forever. You can see it goes up forever. But what happens is you'll notice that this doesn't actually go below the x-axis. Why is that? And what does that do as far as our range goes? When we look at this function, y is equal to 5 to the x power, let's just make a table and look at what actually happens and why our domain and range exactly are, or why they are exactly what they are. I could put in any value for x. 0, 1, and 2, I could put these in. I'm going to get values. I just end up with 5 to the 0 power, which will equal 1. 5 to the first power, which will equal 5. 5 to the second power, which will equal 25. And you can see that this grows very quickly, right? What about when we put in negative values here? Okay, I'm going to move myself over here out of the way. What about when I put in a negative exponent? Let's say I put in a negative 1 or a negative 2 or even a negative 3. What ends up happening? Well, I put in 5 to the negative 1, and that means we end up with 1 over 5. And then I put in a 5 to the negative 2, and we end up with 1 over 5 to the second, which is 1 over 25. And then I put in 5 to the negative 3, and we end up with 1 over 5 to the negative 3, which is 1 over 125. And what you'll notice is that no matter whether I put a positive or negative value in here, I never end up with an actual negative y value. In fact, what happens is that value, that 1 over 5, 1 over 25, 1 over 125, it just becomes an exponentially larger denominator, which means my decimal just eventually just keeps going 0, 0, 0, 0, 1, and then 0, 0, 0, 0, 0, 0, 1. And it gets exponentially, infinitely smaller as it approaches 0. So what does that mean in terms of my domain and range then? Well, my domain for this, when we look at this, is that it goes to the left forever, because I could put any x value in and get a y value. And it goes to the right forever, same thing. But as far as the range goes, it will go from infinity, because it goes up forever, and it'll stop at 0. And when we looked at our graph, you can see that the graph was doing this, like that. Just approximation, okay? Well, if we remember anything about inverses, what ends up happening is when we solve for the x and y, when we switch the x and the y and we solve for y again, we end up taking the domain and the range and swapping their places. And what's going to happen is our domain for a log function is going to be 0 to infinity, and then my range is going to be negative infinity to infinity. Remember, this happens whenever we take and we do the inverse, which is just switching x and y. So if that's the case, when I look at this picture, we should see a reflection over y is equal to x, because x and y switch places. The original graph that we saw was this graph right here. Well, if we see its reflection, it should actually go down here. Let's see if that's what happens. Okay, let's turn this one off. There's y is equal to 5 to the x power. There's y is equal to x is in the middle, and there's the reflection where it's log base 5 of x. So it reflects directly over that. And we can look at the domain, and we can see it stops at 0 right there, but then it goes to the right forever. And we look at the range, we can see that it goes up forever, because it's technically, when we look at the end behavior here, it is going to the right, but it's also going up. And when we look at the left side here, it's going left, but it stops at 0, but it goes down forever. Okay? So there's our domain and range. Now let's talk about restrictions on our domain and range. Okay? This right here, we already said it. I'm never going to get a negative value here. Okay? There's no value that I could put in for x up there that's going to give me a negative value overall. We'll just get a decimal. So what happens is that creates a domain restriction here with these problems where x minus 7 can't be less than 0. Okay? It's going to be greater than 0. We even said over here that no matter what I put in for my x value, I will never get 0. I will just get a decimal that really gets small and close to 0, but never actually equals 0. And so we say that x minus 7 is going to have to be greater than 0, not equal to 0. So that means that x simply has to be greater than 7 in this instance. So as far as how that impacts my domain and my domain is no longer at 0. Now it's going to be shifted because that x minus 7 means it shifts the graph to the right 7. And now my domain would be from 7 to infinity. And the range of this is still going to be negative infinity to infinity because all I did was I moved my curve, which was this. I moved my curve to the right 7. I didn't change the up and the down direction of it. Okay? All right, so let's review some basic properties of logs. Okay, and there's several of them that you need to know, and there's a lot of redundancies in these. Some of them kind of piggyback off each other, just like exponent rules. All right, here's the first one. Log base b of a is equal to x. Now this is hands down the most important one. This is the one that allows us to switch back and forth between log and exponent. This is our log notation. This is going to be exponent notation, converting back and forth. You ready? Whenever we're looking at these, our bases are going to be exactly the same. So whatever the base is on the one, the base is the same on the other. That's probably not the best thing to use. The bases are always going to be exactly the same. B is always B. What's going to happen is we're going to take and we're going to go ahead and swap these two values. We'll always just swap places when we're going back and forth. So the base will always be the base. The x and the a will always just swap places. So it's going to be x will become an exponent there, and a will be what we equal, and vice versa. Okay? It always just bounces back and forth. All right? That's the first property that we need to know. The next property we need to know is if I have log base b of a is equal to x, okay, we can simply take this exponent that's right here and we can move it to the front. Okay, this is called a power rule. And that means that the simplified form for this would be x log base b of a. Okay, so that's a second property right there. Another property is log base b of a. And this one is generally used on like calculators where you don't have the log function built into it. Instead, you would have to do change of base. On our calculator, we do have a log function built into it. So if we look at like even just a graphing calculator here, okay, ooh, oh my gosh, what's happening there? Okay, if we look at the calculator here, we look for the buttons for log. There's a couple buttons that we need to know. The log buttons are right here in the middle of our screen. And then there's another button that we can actually use. Sorry, they're not in the middle of the screen. They're right here next to our numbers. You'll see them there. Oh, I'm cutting out there. There's another button that you can actually use, which is in the alpha and then window right here. Oh my gosh. Okay. And if you go down to right there, you'll see it says log base. It's the last option on the bottom there. You can use log base, and it'll actually give you a base and the portion of. Okay. So that's another option with logs. But change of base is literally converting it so it becomes base 10. So the conversion for this is log of b divided by log of a. Nope, totally just wrote that wrong. Log of a, my gosh. Log of, you could tell it's early. Log of a divided by log of b. Okay? That's called the change of base property. So that's an important one to know as well. Okay? We got this property here. And this property here. We got a couple more. We got 4 more that we're going to actually work through. Okay? Log base b of 1. Okay? The rule for this one is that it's just going to equal 0. Well, why is that? That actually piggybacks off of that very first rule that we just did, the log base b of a. Look at what happens and why this actually takes place. Okay? That log base anything of 1. So if we have that 1 there, it's always going to equal 0. The rationale is that if I did the conversion, b is the base, and remember what's going to happen is these two will swap places, so I put a 1 here and a 0 here. I'm sorry. If I swap their places, I put a 0 here and a 1 here, anything to the 0 power is simply going to equal 1. So b to 0 equals 1. That's just using that very first rule that we established earlier. Okay? All right, the next one is what we call a one-to-one property, and that's when we have log base b of x is equal to log base b of y. And what that says is that once I look at the bases being exactly the same, and I've got one term over here and one term over here, because it's a one-to-one, we can ignore everything and just focus on the fact that x should equal y. Okay? The same property is actually going to be true for this if I have an exponent where it's a to the x is equal to a to the y. Once we look at this and we know we have only one term and only one term here, we have a one-to-one. Okay? Once we have a one-to-one property, we can ignore all the bases and everything and just say that x is simply equal to y and solve for y. And then there's a really important one that we need to know. All right, and this goes back to just basic algebra, that if a 1 over x to the negative 5, that's the same as x to the fifth, and vice versa, that any negative exponent just switches around. So let's just practice solving these. And again, I'd rather not sit here and focus on properties so much. There's really only one you need to know. But I'm going to show you a couple of different ways to solve these, where you can do these very quickly mentally, or you can go ahead and use conversions, but I'll show you both ways just so you can get acclimated to both of them, okay? So log base 3 of 81, this one's simply going to equal 4, okay? Why is this? Well, when you're looking at this and you say log base 3 of 81, what does it equal? What does it equal? What you're saying is, you're asking what does it equal? You're saying equals x. Well, the conversion, if I was to do this, the base stays the base, so we're going to have 3. And then what's going to happen is these two will swap places. So this is going to be x, and this is going to equal 81. And now you can mentally do this, okay? Again, this is where I said there's so many different ways you can go about this. It's just, you'll figure out over time which one's easiest. You would say to yourself, 3 to what power is equal to 81? Well, that means that x is simply going to equal 4. Let's say I want to use the one-to-one property. 3 to the x is equal to 81. 3 to the x is equal to 3 to the fourth. Well, drop the bases and it just becomes x equals 4. We can do that. You can use your power rule. Watch this. Log base 3 of 81 is the same as log base 3 of 3 to the fourth power. And what happens is when I use this 4 and move it to the front, this will become 4 log base 3 of 3. Well, if I use my change of base formula, this is 4 times log of 3 divided by log of 3. And log of 3 divided by log of 3 is just 1, so this equals 4. So this is what I was saying, is that like all these rules have a lot of redundancies to them. It's just ways of working through problems. Quickly or slowly, it depends. It's trial and error to get used to like what's the fastest and easiest method. This is why it's important to work with people, because you may see it one way, somebody else sees it another, and that way it might actually be a little bit easier. Okay, let's try this one. This one's going to equal negative 4. Why? Well, if I go ahead and do, let's just practice doing the change. The base will stay the base, so this will be 2. And then we will go ahead and swap these two places here. So that means we're going to have x and 1/16. Now, generally when you're doing these, you don't want to end up with x in the exponent. Usually, once you get the x out of the exponent, you just throw it in the calculator. But I'm just showing you how to do these by hand. This 16, 1 over 16, is really 1 over 2 to the fourth, which means we get 2 to the x is equal to 2 to the negative 4. Which means that x simply equals negative 4. Okay? This is just one way to do it. Numerous ways to tackle it. But again, once x is isolated, generally you could just throw that into the calculator and move on with your life. Okay? All right, whoops. You didn't see this. You didn't see this. Forgot to delete that, sorry. All right, log base 7 of 1. This is one of our properties we said earlier, that this is simply going to equal 0. Why does this equal 0? Well, again, the rationale is that if I keep the base, and I say to you log base 7 of 1 is equal to what? We're saying it's equal to x. That means that this is going to be, this is going to end up being 7 to the x is equal to 1, and 7 to the 0 power is equal to 1. So that means that x is simply equal to 0. Okay? What about this one right here? Now, I'm going to have you take note of the fact that this one actually is going to have a restriction placed on it. We look at this first and say that this is, in fact, a one-to-one property. Okay, this is a 1, and this is 1. If it's not 1 to 1, what's going to happen is we're going to end up having to do condensing of these, and we'll do some of those later on. For right now, it's just a 1 to 1. When it is a 1 to 1, we can simply ignore the log base and just focus on the inside part. So that x minus 5 is going to have to equal 3x plus 2. Now, before we finish solving this, let's talk about something. We have domain restrictions in this problem. If you recall, whenever we have a log, we said that there has to be a restriction placed on that internal value, that x minus 5 has to be greater than 0. So that tells us that x has to be greater than 5. So when we solve this, whatever we get, x has to be bigger than 5. Over on the right side, 3x plus 2 has to be greater than 0. That means that x has to be greater than negative 2 over 3. Now, when you look at this, we have two restrictions. We have when x is greater than 5, and we have when x is greater than negative 2/3. That greater than 5 supersedes that negative 2/3. Here's why. If we think of it in terms of a number line, and I put a negative 2/3 here, and I say 5 over here, and I say my answers have to be this way, and then we say, nope, negative 2/3 is this way, anything that is over on this side is not going to work because of this restriction right here. So if I said 0, let's say x is 0. 0 is not greater than 5. So 0 gets taken off the table. If I put in a 1, 1 is not greater than 5. If I put in a 2, 2 is not greater than 5. So this greater than 5 supersedes everything over to the left of it, and my restriction on this is that whatever I get, x has to be greater than 5. So let's see what happens here. Let's check our work. We're going to end up with a negative 2x is equal to positive 7. So we get x is equal to negative 3 over 5. Now, x is not greater than 5 here. So this is not a solution. We would say no solution. Why is this? Because when we put in log base 8 of negative 3 over 5 minus 5, and we check this, you can actually put this into the calculator and check it, you get negative 17 over 2. We can't have a negative value there. You're supposed to have a value that's greater than 0. That's not greater than 0, therefore we have no solution for this problem. Okay? All right, let's continue on. Natural logs and E. All right. So I'm going to give you a couple problems here just for extra practice so that we can understand where things are at. All right. Log base 10, well, log of 8, what does it equal? Let's just practice using calculators for this stuff. Log of 8 equals, when we don't have a base written here, log's base is always a base 10 unless it says otherwise. So base 10 is what we use when we're talking about the orders of magnitude, when we're talking about earthquakes, and we're talking about the Richter scale with that. So base 10 though for log is always the base that we use whenever there's not one written. Okay, throw this in your calculator. We're going to get 0.903 and then a bunch of decimals. Okay, if I was to do log base 5 of 7, again, throw this in your calculator, make sure you can get it. It's 1.209. Okay. When we do natural log is something that is actually used when we're dealing with an E in a problem. And this is 1.791759. E is always the base of natural log. You will never see a different base of natural log other than E. Okay. And I'll talk about E in 1 second, where it actually comes from. But this is on your calculator as well. You should know where this is from previous experience, but it's right next to the number 4, and it's above your natural log. This is E to the 4th power, would be 54.598, so on and so forth. We'll get to E. We'll talk about E in a second. All right? So make sure you know how to put these things in the calculator because this is a very calculator-intense unit. So let's talk about the applications of this, okay? One of the most familiar examples of exponential growth is when we talk about taking an investment and compounding interest over time. Interest means money that's given to you when you put something in at a certain rate. Like, let's say I gave you $10, and at the end of a year, you're going to owe me $10 plus an additional $1. What does this look like? Well, when we look at a problem, we look at, it says, suppose principal P is invested at an annual interest rate R, compounded once a year, If the interest is added to the principal at the end of the year, then the new balance P1 is the new balance. P is my principal. Principal is whatever you start with. So when I get a mortgage, the principal balance is how much money I owe. When I buy a car, the principal balance is what I owe. So it's always that initial amount. The PR, when we're looking at this, is the interest earned. Okay? And so it's always going to be your rate times the principal. So if it's 5% and my principal is 100, I'm going to owe 100 plus an additional $5. So what we do is we factor out this P, and we end up with a formula that says P times 1 plus R. And this formula is the formula we use when we're talking about taking an interest rate, compounding it only one time a year for only 1 year. But what happens when we're compounding it over time, multiple times? Then the interest rate compounds R divided by N, and the account balance over T years is given, and the formula itself actually changes. So what we have is P is the original amount, R is the rate as a decimal. You do not use the whole number. So for example, if I said 5%, you don't use 5%. You use the decimal of this, which is 0.05. Okay, the most common mistake that people make with this is they put in a 5, which is technically then saying it's 500%, not 5%. N is the number of times. Okay, and we'll go over some examples of number of times. And then T is the time in years. And then the last value in here is A, which is the end amount. Okay, so how much you have after a certain period of time. So let's just look at some basic examples here. Okay, if you took $500, you invested it into an account garnering 3% interest, meaning you're gaining 3% interest, how much will be in the account after 6 years if compounded regularly? I'm going to go on a tangent here and just tell you guys something about interest. I wish I had listened to my father when I was a kid. He had told me to invest. I didn't invest right away. I was too busy spending money because that's what teenagers do. And I missed out on becoming a millionaire. I'll show you why in a minute when we get to the bottom here. But invest as soon as you can. Invest. Don't just leave money sitting in a checking or savings account. Put it into some sort of account, a retirement account that earns more than your 0.1% interest that's sitting in your checking and savings account. Here's why. If I take $500 and I put it in quarterly, that means it happens 4 times a year. I'm going to have A is equal to 500 times 1 plus 0.04 divided by 4 raised to the 4 times 6. And if we put this into our calculator, you're going to end up with $598.21. Now, what this means is that I put 500 in. And at the end of 6 years, I don't even touch it. I do nothing to it. I now have $598.21. I have made $98.21 by doing nothing. So what happens when I go ahead and start increasing the number of times interest is happening? Logically, you would say it's going to grow, and it's going to grow a whole lot more, right? Well, when I put in monthly, which is, I hope you know this, there's 12 months, what's going to happen is the formula is going to change. We're going to have 500, 1 plus 0.04 divided by 12, raised to the 12 times 6. So we're going to get interest compounded 72 times over the life of it, 72. But what's happening is that interest rate's being broken into 12 pieces. So what ends up happening is our interest on this is only we're going to be at $588.47. So I made like an extra 26 cents by letting it compound monthly. Yippee. Right? What about weekly? You would think it'd be a whole lot more when there's 52 weeks, right? 52 weeks equals weekly. Well, if I do that, we're going to end up with 598.58. Not a whole lot more. If I do daily, there's 365 days in a year. Technically, there's 365 and a quarter if you count leap year. And we end up with 598.60. And then what happens if we do every minute? Every single minute, right? Minute. Well, there's a song from the movie Rent called Seasons of Love, and they sing 525,600 minutes. 525,000 moments so dear. That's the number of minutes that are in a year. And if I do that, we're going to be at 598.61. And there's a famous mathematician, Bernoulli, who discovered that if you were compounding interest regularly over time, what's going to happen is you stop earning as much as you would think you would over the duration of 1 year. What he found was that if you were to take $1 and invest it at 100% interest, at the end of 1 year, you would have $2. Okay? And then if you took, and let's say instead you did the $1, and that's if you only did it one time for the year, and you did it twice a year, you would end up with $2.25. And if you took $1 and did it quarterly, you would end up with $2.44. And if you took $1 and you did this 12 times a year, you would end up with 2.61. And if you took $1 and you did this 52 times, you'd have 2.69. And if you had $1 and you did this over 525,600 minutes, what ends up happening is you approach this value, which is 2.718. That's an interesting value. That is a very wildly popular value. Not as popular as pi, but it's a very popular value. This value is what we call E. So Bernoulli was the one that discovered this, and Euler was the one that actually coined it as E. He probably used E because it had to do with his name, Euler. And where does this come from? Well, this is calculus. This is where limits are coming into play. He found that the limit as x got really, not x, as n got really large, as n approached infinity, what ended up happening was 1 plus 1 over n. So this is if I took at 100% interest rate, 100% interest rate here, and I divided by n, as n gets really large, we're going to have n times, which is infinity. Because remember, it's n times t. T doesn't matter here because as n gets really large, it's going to approach infinity, right? And what he found is that as I do this, we go ahead and we end up with 2.718, which is what E is equal to. Okay? And so this changed our formula. We said if we're constantly earning interest, infinitely earning interest over time, that the formula becomes A equals P E R T. And no longer do we use the N and all that stuff. It's compounded continuously. The R is still your rate. P is your starting amount. T equals your time. All right. So let's jump back into this final portion here. Okay. And the idea of investing. Let's look at two scenarios here. Okay. Ben is somebody that takes and invests, and he starts investing at the age of 19. Okay. At the age of 19, he puts in $2,000, and he does this for 8 years. So he's going to put in a total of $16,000 total. And he's going to be earning 12% interest. Now, there are places that you're going to earn 12%. Put in a retirement account. You'll see that I think Vanguard has some that are earning over 12%. But 12%. $2,000, if you divide that by by 12, 2,000 divided by 12, you're going to be putting in $167 per month into your retirement account. That's it. $16,000, $167 a month for 8 years. That's it. Arthur, over on the other side here, he never puts money in. He decides to be a normal teenager and just live his life YOLO and goes out partying and drinking with his friends. And he decides to not save until he's 27. He's like, I should really get in on the game here. And he starts at the age of 27 and starts putting money in. Now look at what happens here over time. Okay. At age 27, Ben already has $30,000. At age 27, Arthur has nothing except for that $2,000 he just put in. As we go down here, look at what happens. Ben only put in $16,000, has $2.3 million at the age of 65 by never touching the money. Arthur put in $76,000. He never caught up. He put in $60,000 more and never caught up. He was still $700,000 behind Arthur. Compound interest is extremely valuable to you. It is an important thing. It's something that we should all be aware of and know and use to our benefits when it comes to investing. In the real world, logs and exponents are extremely important. They're a really big part of our world that we live in. We use them for statistical and evaluation when we're talking about normal distribution. We use it when we're talking about the population in biology, and we're talking about what's called logistic growth, which we'll get to later. We use it in physics when we're talking about radioactive decay, and we're talking about half-life of isotopes. It's a big part of our world, you guys, and it's something that you're going to need to know, okay? So, with that said, that completes this lesson. You guys take care. Reach out if you have any questions. Don't overcomplicate these problems. They're all pretty quick. Stay safe, stay responsible, and you guys have a wonderful day, okay?